Right. Good morning. Any questions? Any comments? So I want to start talking about coherent states, and I'll connect the coherent states to lasers, for example, and lasers will be connected to BEC and superfluids, and they'll also be connected to Bose-Einstein condensates. So let me motivate a little bit. So we have been talking about superfluid helium-4, superfluid helium-4, and we have considered Bose-Einstein condensates. Like superconductors. And I actually need to add, since this is not my area, I didn't talk about it, but we can also talk about lasers with a similar framework. And in all of these things, the unifying theme was like a macroscopic wave function. Right? Like there was like a macroscopic coherence we were trying to understand, and this was different from the conventional quantum mechanics. In the conventional quantum mechanics, we have like single particle, like a single electron in the orbit of a hydrogen atom, for example, or like a single electron in a box, and that's the kind of quantum mechanics we are talking about. Here, we have like millions and millions of electrons. They are coming together, or atoms, or helium atoms, and they form exactly the same kind of quantum mechanics we learned in Griffiths, for example, and that's the difficulty of this topic. And the natural language to understand all of these things are something called second quantization, but a friendly entry to second quantization is can be understood through coherent states. Good. Good. Let's talk about coherent states. So the model for, I think this is like a toy model, but I think it is valid for pretty much any physical system, right? We are talking about harmonic oscillator, h p squared over 2m plus 1/2 m omega squared x squared. And here, any physical system is like a harmonic oscillator, right? Especially in the context of quantum mechanics, we are speaking about a wave nature of everything, right? Everything is some kind of wave, like a quantum wave, and wave oscillates. If something oscillates, it's harmonic oscillator. And from that point of view, if you are doing like relativistic field theory, condensed matter, or like atomic physics, quantum optics, it doesn't matter. They're all harmonic oscillators. And you have to generalize these harmonic oscillators to fit the system in your hand. In the condensed matter system, you need to think about a many-body system in the context of harmonic oscillators. In quantum optics, I think they talk about like these modes, like laser modes that are like harmonic oscillators. Also in field theory, right? You have harmonic oscillators, but you have to have like some more technical symmetry, like Lorentz symmetry. In any case, this is the Hamiltonian, and we think about P as an operator, which is minus I h bar d dx. And our job is to solve Schrödinger equation, h psi n is equal to En psi n. And to solve this, we introduce ladder operators. Ladder ops. And there are different ways to introduce this, but I'll use the one in the book. Different books can have sometimes different conventions. So this one is 1 over 2 h bar m omega P minus I m omega x. And similarly, I can define a dagger of this. So this is dagger. The only difference is this is plus, because p and x are Hermitian operators. And these two a's and a daggers obey a dagger a is equal to 1, which comes from xp is equal to I bar. And the nice thing about these operators is, like, if you have like a state psi n of x with some normalization, like some solution, you can hit on it with a dagger and it's going to give you n plus psi n plus 1. And similarly, you can hit on it with n. The only difference is this is n, this is n minus 1. So if one solution is given, you can generate all the other solutions by hitting with a's and a daggers. And if you hit with a dagger a, what you get is, maybe I ask you, what do you get if I hit it n, right? It is like n times psi n of x. And from here, we also write h as h bar omega. Okay, let me define a number operator, which we'll be using in a little bit. So this is a dagger. So I have to be careful and put heads to all operators, but I'm not very careful. I'll forget. But when the context is important, I'll put the heads. Otherwise, I'll not put heads. In all of these contexts, I think it is clear what is operator and what is not. And here, Hamiltonian can be written as n plus a half. Good. And the corresponding eigenvalues, En, h bar omega, n plus a half. So these are numbers, and n can be 0, 1, 2, dot, dot, dot. And we define like a ground state with the property that if you hit on the ground state psi of 0, you should have 0. Why do we require that?
There's no lower state than the ground state.
But why is that? Why should I have like some 0 state like this? What happens if I hit on this and I get, I don't know, psi minus 1, for example?
Your energy is not bounded from below, and this leads to instabilities.
Yes. I mean, it is possible to show this, but I think physical argument is like you shouldn't have like unbounded spectrum from below. And if that's the case, any other state psi n of x can be obtained like this: a dagger to the power n factorial psi 0 of x. And this psi 0 is, so this psi 0 is Gaussian. So let's introduce coherent states. So far everything is undergraduate quantum mechanics, and from now on I think coherent states are not as much known. So let's think about this. Coherent states are defined by like some alpha. So this alpha is a complex number which has real and imaginary parts, or like a norm and a phase, and there's some normalization. It's like psi 0 plus alpha over 1. You read that? Yes. Alpha 1 factorial psi 1 plus alpha squared over 2 factorial psi 2 plus alpha cube over 3 factorial psi 3 dot dot dot. Okay, and we can normalize this. So alpha bra alpha cat is absolute value of c squared, and all of these are normal, right? Orthonormal. Psi 0 is perpendicular to psi 1, psi 1, psi 2, and so on. So this is going to give us 1 plus alpha squared over 1 factorial plus alpha squared to the squared 2 factorial plus, and the same thing, cube 3 factorial dot dot dot, and this thing is going to be equal to c squared e to the alpha squared, and from here we find c to be e to the minus alpha squared over 2. So another way to write this is like, let's rewrite this. So now we know what c is. C is e to the minus alpha squared over 2. And what I can do is I can write this psi 1 as a dagger psi 0 over root 1 factorial. I can write this psi 2 as a dagger squared divided by 2 factorial squared psi 0, and this one similarly. This is a dagger cube divided by 3 factorial psi 0, and then this e to the minus alpha squared over 2. So this is 1 plus a dagger over 1 factorial plus a dagger squared over there's also alpha, so there is alpha squared plus alpha cube, a dagger cube over 3 factorial dot dot dot, hitting on psi. And this series can be summed, and you have e to the minus alpha squared over 2, e to the alpha a dagger hitting on psi 0. And any operator in quantum mechanics, x, is defined as 1 plus x plus x squared over 2 factorial plus dot dot dot. Okay, the most interesting thing about coherent states is, let's consider A acting on alpha, right? And I want to consider this form. Let me copy this form and hit on it with alpha. This is the coherent state, and I'm going to act on it with A. So there's like A here, like A here, here acting on A, here A, and here A. So this thing, what is this? So this one is 0. This one is A times 1 is root 1 psi 0. This one is root 2 psi 1. This one is root 3 psi 2, and so on. Therefore this thing is e to the minus alpha squared over 2, and I can take one alpha outside, this alpha outside, and what remains inside is psi 0 plus 1 alpha is outside, alpha, there is like root 2 here, root 2 here, what remains is root 1 factorial psi 1 plus, similarly 1 alpha is outside, I have alpha squared, root 3 factorial, root 3, what remains is 2 factorial psi 2 dot dot dot, right? And what we see is, actually I can also write this alpha because it's just a complex number to here, and this entire thing is the coherent state. Therefore, what we find is A acting on alpha is equal to alpha alpha. So the coherent states are eigenstates of lowering operator A. Then we can think about the expectation value of A, alpha, A, alpha. Normally things like this are zero, right, in usual number basis, because A is increasing or decreasing number of quanta, and when you increase or decrease the number of quanta, you have a different number of quanta on the right and left, so this becomes zero. But for coherent states, that's not the case. For coherent states, this is alpha times. Then this is, and they are normalized, so this is going to be alpha. I can also think about coherent states with A Dagger A, alpha. And this, maybe it's obvious to you, but the way I do this is I split this part and this part. So this part is alpha times alpha. This part is Hermitian conjugate of this ket, which is alpha star alpha, and alpha alpha are normalized, so this is going to be alpha star alpha, which is alpha squared. Therefore, the expectation value of number operator in coherent states is given by alpha squared. We can also think about A Dagger A, alpha n squared alpha is equal to alpha A Dagger A, A Dagger A, alpha. How do I calculate that?
With an identity in between.
So here?
Yes.
So identity of alphas, yes, but that's more complicated. And I think you can do that as an exercise, because coherent state identity is a little bit different. But for this one, there is like a simpler way. Simpler way is like, I know what alpha does to ket coherent state, right? And what I want to do is I want to carry all the alphas on the ket, and on the A's on the ket, and all the A daggers on the bra. So that, yes, exactly. So this thing using A dagger is equal to 1, or A dagger is equal to 1 plus A dagger A. So that thing becomes is equal to alpha. From 1 I have A dagger A alpha, and the second one is like this: alpha A dagger A alpha. And now I'm happy because now A is acting on ket, A dagger is acting on bra, A's are acting on ket, and A daggers are acting on bra, and we can immediately write the result. So this is alpha squared. We just calculated this. This one is going to be alpha squared alpha. This piece is going to be alpha conjugate squared alpha. The result, we have alpha to the fourth. Then we can look at the variance of delta n is equal to expectation value of n squared minus expectation value of n squared. And this thing is alpha squared plus alpha to the fourth minus alpha to the fourth, and this is alpha. And another thing is if we rewrite the coherent states, so this is alpha is equal to e to the minus alpha squared over 2 psi 0 plus alpha 1 factorial psi 1 plus alpha squared over 2 factorial psi 2 plus alpha cube over 3 factorial, so this is inside psi 3 dot dot dot. And now I can ask what is the probability to have n in the measurement. So if I measure n, probability to find n is like, let me write it like p n. What is it? Let's see if you remember quantum mechanics.
The square of the coefficient.
Exactly. The square of the coefficient is e to the minus alpha squared alpha norm squared divided by 1 factorial. Sorry, not alpha 1 squared. We are looking for nth, and nth is going to be alpha to the nth squared over n factorial. I think that's correct. And I want to write this like alpha squared to the power n, alpha squared to the power n. This Poisson distribution. And in the Poisson distribution, like what we found previously, is delta n is, if you remember, is exactly equal to n, like found above. And if you calculate delta n over n, this is equal to alpha divided by alpha squared. So this is 1 over alpha, and this is 1 over expectation value of n. And what this means is, so here's Poisson distribution. So this is p n. So this is n. So it is something like this. And we have some mean value, which is n. And the width here, so this is the width, delta n is proportional to 1 over root of mean value. Therefore, there is like some uncertainty in the number operator, but as n goes to infinity, and this will be the case of like for us, the case with many particles, which is the subject of this course, right? N goes to infinity, or in the case of laser, it's going to be the case for many photons, many photons. In that limit, delta n, let me write in 2 steps, 1 over root n will go to 0. And in that limit, we can say this n, because the variance goes to 0, this n is kind of like a number. And we are going to use this approximation a lot. There will be operators like n, and then we are going to approximate these operators with numbers based on the analogy with coherent states. So this is like a number. This n is very large, you are right. It is kind of like, but the point is like, yes, it is very large, but the width, right? The uncomfortable thing about this is like, it seems like particles are created and destroyed. You don't have like good number of particles, right? Like n in the harmonic oscillator, we are going to encode it to the number of particles or number of photons. They are very large and they are close to infinity, but the point is the uncertainty, the width is like very tiny. Yes, you can, like n and n plus 1 can be more or less the same in that limit. So let me also talk about the phase of this alpha. Like what about the phase? So alpha, I'm going to write it as like some magnitude times e to the I theta phase. And now let me take this coherent state, not to write the whole thing one more time. So this is and I want to spell out the phase. So here, so this one is going to be alpha e to the I theta. This one is going to be alpha squared e to the I 2 theta. And this one is alpha cube e to the I 3 theta. And what I want to calculate is I want to look at the theta acting on alpha. So if I do this, so this one is going to bring, right? So this is I, derivative of theta is 1. So this one is going to bring I times 2. And this one is going to bring I times 3. And so this I can take it out, but this here, this is n is equal to 1. So here actually there is like n is equal to 0. 0 times I is 0. Here n is equal to 2. This is n is equal to 3. Right? Therefore, so this thing is equal to, so this this del theta alpha is equal to I number operator acting on alpha. Or I can write it like this, 1 over I here and erase this. And from here we see that 1 over I del theta is like number operator. And you should compare this with del minus I h bar del x is equal to p, right? P and x are conjugate variables, and they have this relation. P operator is derivative with respect to x. Exactly, and from here we immediately deduce x and p, they have this commutation relation. Therefore we can also say exactly the same thing. Theta and n, they are going to have this commutation relation. There is no h bar because there is no h bar here. So theta and n are conjugate variables, and that means they are going to have an uncertainty delta n. Uncertainty n times uncertainty in theta should be bigger than or equal to 1 over 2. There is no h bar again because there is no h bar here. And this shows for coherent states n is not well defined, right? N is fuzzy, but theta is sharp, right? Theta is well defined for coherent states, delta n is not. But for the usual harmonic oscillator n states, phase is arbitrary. There is no phase, right? All the harmonic oscillator states psi n, they are defined up to a phase, but number is sharp. Number is well defined. So let's consider two different coherent states. I'm almost done. Hopefully this is not too much, but generally people enjoy these topics, so hopefully I'm not torturing anybody. So let's consider two different coherent states. So I want to consider an alpha and beta, and I want to take their inner product, right? This is how the inner product is defined in the Hilbert space. And for this, I can just spell this out. This is alpha squared over 2 e to the minus beta squared over 2. And in the coherent state, you can see, right, each one comes with alpha, beta comes with beta, but they are one-to-one, right? Each one is orthogonal, so I can just take the product term by term. And this is going to give me 1 plus alpha star beta over 1 factorial plus alpha star beta squared over 2 factorial, and the same thing cube. And dot dot dot. And you can see this is equal to e to the minus alpha squared over 2 minus beta squared over 2 plus alpha star beta. Then the norm of this thing, the norm is this thing. This half is going to go, this half is going to go, this one plus beta star alpha. And this thing can be written as e to the minus alpha minus beta squared, right? Norm square of the first one, second one, alpha star beta plus beta star alpha. And what this says is like, so two different alpha is not orthogonal, right? They are not alpha and beta are not orthogonal, but their overlap decays exponentially. But when alpha minus beta, the distance between them are order of 1, overlap is small, and it decays exponentially. And what it says is like in the complex plane, like so we have like a complex plane. So this is real alpha, this is imaginary alpha, and I have some region for alpha. So this is, let me write it like this. So this is alpha. So this piece is d norm of alpha. Let me try to write this. So d norm of alpha, and this is d theta. And because the norm decays like this, a cell of size 1, area is equal to 1, has approximately 1 state, right? And let's try to see how to understand this. So this, let me write the area. This alpha times d alpha times d theta is approximately 1 state. This area 1 means it's like a one state per area. And we can also connect this to variance in number. Let's say n, we calculated it to be alpha squared. Then dn is equal to 2 alpha d alpha. Okay, there's also a norm here. I can plug this in here, right? Alpha d alpha is equal to dn. Then this is, okay, let me write it like this. Delta n. Delta n. So let me also write this. Delta theta. Delta theta is approximately 1. Therefore, the number of states per unit area is determined by number phase uncertainty. So you have enough states so that number uncertainty is obeyed. And from this point of view, sometimes coherent states are called overcomplete. That's why the identity for coherent states are a little bit different. But there's like an exercise in the book, you can look at it. So to finish, let me connect all of these to lasers and I'll call it a day today. Let's see how this is connected to lasers. And next time I'll talk about superfluids. So in the case of lasers, we also have these A's and A daggers. So we have A dagger and A for lasers. But in the cavity, we have like different wave vectors K. And also we have different polarizations S. Right? And basically you have infinitely many more harmonic oscillators in a given cavity. So this is ladder hops for wave number K and polarization S. Okay? And a quantum state should be defined for all K's, right? So rather, in the previous case, we had something like this, and we constructed the coherent states in terms of these n's. But here we need to think about n k0s, n k1s, n k2s, dot dot dot, and these are all vectors. So each mode, if you want, each wave number mode and each polarization mode has its own harmonic oscillator. And there are infinitely many elements here. And when I act on this cat with a given A dagger, let me call it K, S, there's like dot, 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 dot. There's like a slot here for N, K, S, dot, dot, dot. And what it does is it does exactly what it does for usual harmonic oscillator. This comes like here. Okay, let me open up some space. So this is going to be NKS plus 1. And this one is going to also increase by NKS plus 1. Right, all the others we ignore. So you can do exactly the same thing with the lowering operator A. So it is going to go and find its own slot, and it's going to decrease this one by -1.
But there was NKS plus 1 beforehand, right? I mean, there was already that kind of a quantum number there, and we just generated it.
Yes. So there's always this quantum number, right? For this K mode, there's like this quantum number there, and we went there and we changed it to 1. We reduced it by 1.
But that quantum number has already existed in that state.
Yes. I mean, this state is always there. It may be empty, but it doesn't mean, or it may, if it's empty, this is going to be 0, right? Because NKS is 0.
I mean, what I mean is, we beforehand had this NKS minus 1 state before we applied the ladder operator.
No. For each K, right? You mean like there is like some other slot here with nk minus 1?
Yes.
No, for each k vector, we have its own slot, right? If you want, we can think about these k's like sites, and each k has its own site. And if you increase the photon, you increase the photon in this k. Like you can increase or decrease k, but increasing or decreasing k will take you to a different cell here. Each cell has its own harmonic oscillator. And when we increase or decrease, we need to go and look for the correct slot. So this k can do nothing about another. Like say there is like k minus delta k mode here. This k minus delta k mode has nothing to do with this operator. Okay? So that's important. And also these can be encoded in the commutation relations rather than looking at all of these things. If you just write a ks a k prime s prime dagger, right? So this thing is, it was normally 1, but now we have indices. This is going to be delta ks k prime s prime. What this says is like two different modes, k prime and k. If they are different, they don't know anything about each other. So they commute with each other. And this also shows us these are bosonic modes. Right? Because these two modes, take them and interchange, they interchange without any effect, so they are bosonic. And all the other commutation relations are not important, but let me just copy and write them to make sure. So if this is like that, or like that, no matter what k and k prime are, these are 0. And laser is easy to write, so lasers are coherent states. Let me write this and then finish it there. It is kind of like the same thing, but now there are different alpha, K0, S0, alpha, K1. Right now each K mode is going to have its own coherent state, S1, and dot dot dot. And this is written like e to the minus a half sum over all k's and s alpha ks squared, and there's this e to the ks alpha ks a ks, and this entire thing is acting on vacuum. So this is vacuum with no photons in it. So this is no photons. And typically in a coherent state or in laser, one mode is macroscopically occupied. What this means is like NKS is something like alpha ks squared is a large number, and all the others are empty. But of course this is like a mathematical requirement. In real life, in the cavity, there are like non-linear effects. Like, I don't know, we are doing some optical pumping, there's like some matter and light interactions. I don't know the details, but because of these like unwanted effects, there are like non-linearities, and these non-linearities drive occupation in the vicinity of K. They are typically unwanted, but people can make this really, really sharp and very, very nice coherent state. And this is what we call coherent laser. And we'll see, for example, Bose-Einstein condensates are also like this, but rather than populating these K modes with photon, we are going to populate them with atoms. And in the case of superconductors, we are going to populate these K modes with Cooper pairs. and we are going to try to understand like a macroscopic wave function. But unlike what we did so far, we are not going to do phenomenology. We are going to do microscopic calculations. Okay, that's the goal. Good. All right. Any questions? Thank you.